Hey folks, thanks for sticking around for the final sessions. My name is Max and I'm going to give you an introduction into the Flink dynamic Iceberg sync. So this is going to be maybe slightly more technical talk, but I hope you'll enjoy it. And yeah, so why the dynamic sync? So this was a heavily requested feature from many Iceberg users because they were often frustrated about the complications of writing to multiple Iceberg tables and also handling schema updates and spec updates and write pattern changes. So yeah, as we will learn, the dynamic Iceberg sync solves all of these issues. But to get started, let's first talk about the limitations of the Iceberg sync. And when I refer to Iceberg sync, I mean Flink Iceberg sync. This is a very Flink, it's a little bit Flink-centered talk. I hope you all like Flink. Yeah, so, but like theoretically, I mean, this could apply to other execution engines, but currently it's only available for Flink. So, but yeah, this is going to be an effort also to like generalize it so like other execution engines can make use of it. So generally with the Iceberg sync, there's if you want to use it, there's just you need to use one instance per table. And this obviously makes like writing to multiple tables a little bit complicated. When you have changes to the table, like table name, schema, partition spec, and so on, those are not picked up automatically because when the Flink job starts, those like the schema and the spec and so on, they are like loaded from the catalog, and then yeah, basically you cannot change them unless you restart your Flink job, and then it will pick up the changes. And similarly, if you need to change the write parallelism, you want to use a different distribution mode, you want to turn on upserts, and so on. Yeah, you need to configure that, and it requires Flink job start. So if we compare now, like the old and new sync, so yeah, we have like overly simplified, but one table per sync, you cannot really create new tables. You have fixed metadata, fixed write pattern. But then to the rescue comes the dynamic Iceberg sync. So there we actually support unlimited number of tables per sync. And you can dynamically create tables. You can on the fly change schema, partition spec, and so on. You can also like dynamically route data to different to tables like as you wish, and change the distribution mode, write parallelism, and so on. Basically all the things you would normally statically configure. Now I want to maybe highlight a little bit the architectural differences. So in the old current Iceberg sync, in Flink Iceberg sync, you have row data as input. Row data is Flink's row data format, data structure, and then you send that to the writers, and writer tasks, or we say subtasks in Flink, so basically like workers who write the files, and then you emit a write result from each of the writers, and this is aggregated at a single worker, and then sent downstream to the committer, which also runs in a single worker. So with the dynamic sync, it is, this part is mostly the same, but here in the front, it changes a little bit. So you have, instead of row data, you have actually arbitrary input type. And that is because here in this first operator, you define your own function, like generator function, which generates dynamic records. And we will see how dynamic record looks like, but it's essentially, it contains all the data you need, schema, spec, table name, and so on, to then like perform a write. And because you have multiple tables that you're writing to, you need to distribute the data somehow in the cluster, and you have you do this by a write key. We will take a look at how the write key is generated, and yeah, and in the end you just key by table name, so you end up like in a single worker where you do your aggregation, and committing. And yeah, because we we continuously need to interact with the Iceberg catalog, because not only at job start, we maintain a connection here to the catalog. Actually, not only here, but okay, but let's just use this as an example. And so when we see like a new schema and we compare it and to the existing table schema, and then we also update via the catalog. And yeah, let's just look at the write key for now. So the goal is, of course, to be able to write thousands of tables inside a single Flink job. So to achieve that, we need to distribute the writes across the workers, the Flink subtasks. And yeah, because the parallelism itself is dynamically configured in the dynamic record, we need to somehow come up with a way to distribute the data. And for that, we pick a set of random, well, deterministically random subtasks, and then we use that subset to like round robin distribute with if distribution mode is none, or do a hash-based distribution, but only on this subset of subtasks. So this allows us to like write at a lower, like if your job parallelism is, for example, 100, you can actually write tables with parallelism 10, and you can do this with as many tables as you like, and they will all like end up on a different set of subtasks, so you have some load balancing across the Flink job. So yeah, there's one issue with this architecture, and it's that we need to do a lookup here to check what's the current table's metadata, but we also need to update, and this can put a lot of, I mean, we don't look up very often. I mean, we do caching and we refresh every once in a while, but for updates, this can cause quite a lot of load, because when there's a new schema arriving at 100 different workers, then they will all call out to the catalog and try to update the schema. And of course, just one of them will succeed, but still puts a lot of load on the catalog. So to prevent that, we have this special, this other mode that users can use. So if we know this, if the schema is known and then we can, and not hasn't changed, we just proceed with normal path. But if we need to update this, we key all the data by the table name. So we basically reroute all the data to a single worker temporarily, where we will then perform the schema update, and then we continue. And yeah, this has also some downtimes because it can change the order of the records that are being processed, so it is not optimal for certain use cases like CDC, but for a lot of others it is. And you can always use the immediate update path if you require strict order guarantees. So let's take a look at the API. So it looks very similar to the existing Iceberg sync. You specify your input, you have your generator, you have your catalog loader, and there's some more options, but stick with those for now. And then there is the generator function. This might be a little bit too small, but it's basically just one interface to implement where you have your input type, and then you have a collector, that's a Flink thing, of dynamic records, so you can like emit 0, 1, or more dynamic records. And dynamic record looks like this. So you have all the things that you would normally specify, table name, round schema spec, and the data itself is still stored in raw data format. But I mean, there are tools to convert from other formats. Yeah, and yeah. then you have these write-related options as well here. So let's talk a little bit about schema evolution. When we receive a schema, we need to compare it against the current table schema, or actually we compare against all the existing table schemas. And if we find one that matches exactly, that's fine, and we can use it directly. But if there's some divergence, then we can actually, in many cases, adapt the input schema to, slightly such that it matches the table schema, and we also change the data in that case. So for example, if the table schema contains an additional field that is optional, then we can just null that field and add it to the data. And yeah, we don't need to go to the catalog for that. And otherwise, we call out to the catalog and we do the updates necessary. And yeah, we always compare fields by name, not via field IDs. I think the initial version used field IDs, but we quickly came to realize that it's a little bit too much to ask for users to correctly identify the field IDs of Iceberg schema. So yeah, we use names, and that's also what Iceberg APIs use. Yeah, I think that makes sense. So yeah, the conversion part I mentioned is, yeah, we support these operations. We can reorder fields. We can do type widening. Like, for example, if I receive some data which has int, I can widen that to long, but that's good because I don't want to change the table schema from long to int, because that would obviously cause some data loss. And yeah, I mentioned the null values for optional columns. So what kind of updates do we support? We support basically everything that also Iceberg supports. But we're a little bit, yeah, we want to be non-breaking. That's why we just, at the moment, support adding new columns, updating or widening the type, adding like any non-breaking updates, adding new fields to a struct, and reordering. We don't allow dropping columns or fields, and we don't now allow renaming. So renaming we cannot actually do because we identify by name. So yeah, I mean, that's tricky to do then. And dropping columns is problematic because once we drop a column and we read some data later that references that column, then we would have to recreate it, and that's not really possible because it would be a completely new field. So that's why we're on the safe side. Maybe we will have a mode where we also allow dropping fields, but for now, no. Yeah, for partition spec evolution, it's pretty similar. We support like adding, removing transforms, and we do some yeah, fancy. So we always use actually the table schema. Like we never directly take the user schema. And so we do have to do some rewriting of the specs. Since the spec is bound to a schema, we need to rewrite them to make sure they reference the correct fields. Yeah, so there's some implementation detail here. So then, yeah, to do all of this efficiently, there's some caches to cache table metadata, key selectors for distributing data, serializers, and of course writers, task writer. And yeah, we did a bit of benchmarking I wanted to show. This is part of the open source code, so you can run this benchmark. We compared dynamic sync against the regular sync, and we found after some optimization that there's some overhead, but it's quite small, and there's already some, this is not completely up to date because there's already some improvements being made by the community, and I think we're even down further, but yeah, you can see there's small overhead, but it's overall not too dramatic, and Also, the real powerful thing is like writing to multiple tables, which you can only do with a dynamic sync. So yeah, actually, we before we optimized, we had about like 100%, 100% the runtime. So we did some optimization there. For example, what we found was that if we use for the caches, if we use a maximum size instead of like a time-based expiration of the caches, we would dramatically improve the performance. Same for using Flink's row data serializer versus using Avro. This is a huge performance improvement. And also like caching the schema comparison results, because like, comparing schemas is sort of expensive. We do it on a per record basis. That is also good, yeah. And yeah, there's also benchmark to write to multiple tables. And yeah, what we've seen there is if you write a very small amount of tables, because the way we distributed the writes in the Flink cluster, there can be some clustering for a low number of tables. So yeah, if you need to increase the, like for smaller tables, you need to increase the write parallelism. But it's probably not so much a concern if you're actually writing to a lot of tables. So wrapping up, use the Flink dynamic Iceberg sync. Yeah, if you want to write to multiple tables, dynamically create and modify tables. And yeah, seamlessly migrate schema and partition spec without any like external intervention. And you want to programmatically control the table write pattern in your code. And yeah, do all of this without having to restart a Flink job, basically with zero downtime, hopefully. So yeah, some references. There's a design doc. I don't know who knows Peter Very, but he worked a bunch on this. And yeah, he's very active in Iceberg. And there's also the upstream PR, which got broken down into a bunch of others, if you want to check it out. So that's my talk. Thank you.
Thank you, Max. Are there any questions? Yes.
Do you have any benchmark on comparison with some other approach, like maybe Kafka Connect with Iceberg that is come with official also? Or is there any pitfall between using connector versus this Flink approach?
Yeah, that's a good question. We don't have any, I mean, I'm not aware of any benchmarks, but I would suspect that, I mean, that is quite a bit slower going through a Kafka topic. I mean, that's just my gut feeling. But yeah, it would be interesting to do such comparison and like post it on a mailing list. That would be exciting.
Yeah, question from here. Can you get to your benchmarks spec?
Yeah.
These numbers, are they for append operations or is this for absurd as well?
Oh, these are appends. Is
it fast append or is it, there are two types of appends you can do in Iceberg.
That's a good question.
The reason I'm asking is because, so we worked on sort of Iceberg sync, right? And but we only append one set of data for our staging tables, and it takes less time than that. So I was wondering why is that? But we do fast append.
When you say less time, I mean broken down to the record, or did you just divide the time by 5 million?
Essentially, so let's say we take 5 million records. What we do, we create a set of Iceberg compatible Parquet files from that, and then fast append them to the table, and the table is empty in that case. And that operation for 5 million rows takes like 2-3 seconds.
Okay, I mean, I guess it depends like how large the rows are, but yeah.
What is the like the size of the data set here in terms of number of columns in it?
I could look it up. I mean, it's in the source code. We can take it offline and.
Maybe one follow-up question. So how does it actually degrade depending on how wide your data set is? Because at least our experience is that the Iceberg write performance degrades pretty rapidly with the, let's say if we move from 50 field table to 400 field table when we're trying to write a batch to it. Do you have any kind of also tips and tricks? What can be done in that case?
Again, very good question. Like these are, I think these are like 10 to 20 fields or so. I don't know exactly. I need to, it's a long time since I looked in the code, but I don't have any specific performance tips for like dealing with like large number of fields.
Yeah, the reason I'm asking about this because we deal with a lot of like Microsoft design systems and they love to just generate very wide tables. So for example, Microsoft Dynamics contact table has like 400 plus fields in it. And it's a nightmare to like stream it efficiently. So I'm also like fishing for what people do with these kind of crazy data sets.
Yeah. So, yeah, it's a good
Maybe
question.
we can talk afterwards a bit.
Yeah.
That's a good thing. So Max, thank you very much for your talk. Guys, small applause.